NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will simplify a compound radical expression, carefully following a clean step-by-step algorithm and keeping every transformation clear. Here is the expression we will simplify. We'll transform each term and then combine. Step 1. Focus on the first purple term. The trick is to express the plane 2 as a sixth root of 2 to the sixth, and then combine inside a single sixth root. After that, a fifth root of a sixth root becomes a 30th root. Finally, simplify the power of 2 and reduce the index to get a 10th root of 8. Step 2. Now the orange term. The fifth root of square root 2 equals 2 to the 1 over 10. Raising to the third power gives 2 to the 3 over 10, which is again the 10th root of 8. Step 3. The blue term 2 to the 3/10 is already in power form, and we rewrite it as the 10th root of 2 cubed, the 10th root of 8. Step 4. For the green nested radical, 10th root of 8. Step 4. For the green nested radical, use the identity square root of a plus 2 times square root of b equals square root x plus square root y, when x plus y equals a, and x times y equals b. With a equals 4 and b equals 3, we get x equals 1 and y equals 3, so the expression becomes square root 3 plus 1. Now combine all terms. The first two produce a 10th root of 8 plus a 10th root of 8, and we subtract 1/10th root of 8 from the blue term. That leaves a single 10th root of 8. The red term remains as the 40th root of 128, and the green term simplifies to square root 3 plus 1. Final answer. The 10th root of 8 minus the 40th root of 128 plus square root 3 plus 1. We reached this by aligning radicals to common indices, converting powers to roots, and using the classic nested radical identity. Radicals to common indices, converting powers to roots, and using the classic nested radical identity. We will prove a radical identity step by step following the given algorithm. We want to show that b times square root of 2 multiplied by the fraction equals the square root of a plus b quantity cubed minus the square root of a minus b quantity cubed. Step 1. Express the denominator. The square root of a plus the square root of a squared minus b squared equals the sum of the two half radicals with absolute value of b. Step 2. Let capital A be the left-hand side. Substitute the denominator we just found. Factor the 1 over square root of 2 from the denominator to get 2b in front. Then multiply numerator and denominator by the conjugate, that is, the difference of the same radicals. The product of the sum and difference gives a difference of squares. The denominator becomes 2 times the absolute value of b. Simplifying yields b over absolute b times the two factors in the numerator. Use the identity square root of a squared minus b squared equals the square root of a minus absolute b times a plus absolute b. Then split 2 as a plus absolute b plus a minus absolute b. Collect the terms in brackets, and notice the sum times the difference gives the difference of cubes in radical form. That yields the cube pattern of the two square roots. Finally, analyze the sign of b. If b is positive, absolute b equals b. If b is negative, absolute b equals negative b, and the order of terms flips, giving the same final expression. Therefore, for a greater than the absolute value of b, the identity holds exactly as required. In this lesson, we build intuition for when two radical expressions are equal and how to decompose or simplify nested radicals using term-by-term matching. We'll end with a fully worked example, simplifying the square root of 18 plus 12 times the square root of 2. First key idea. If an expression contains a non-radical part and a radical part, equality requires the matching parts to be equal. For example, x plus square root of y equals x prime plus square root of y prime. This forces x to equal x prime and y to equal y prime. The same idea extends to sums of unlike radicals. If we have a whole part, a square root part, and a cube root part, equality means each corresponding kind must match. To decompose a nested radical like the nth root of an expression with simpler radicals, we assume it equals a sum with unknown coefficients. Then raise both sides to the h root of an expression with simpler radicals. We assume it equals a sum with unknown coefficients. Then raise both sides to the nth power and match the like radical parts. This turns a complicated radical into a solvable system. Let's do a clean example together. We will simplify the square root of 18 plus 12 times the square root of 2. The classic trick is to guess it equals the sum of two simple square roots. Then we square and match parts. Now square both sides. On the left, we simply get 18 plus 12 root 2. On the right, we get m plus n plus 2 times the square root of mn. Because the non-radical and radical parts must match, we obtain a system of two equations. From the second equation, divide by 2 the square root of mn equals 6 root 2. So mn equals 72. Now solve m plus n equals 18, and mn equals 72. That quadratic factors as t squared minus 18t plus 72 equals 0, giving t equals 12 or 6. So m is 12 and n is 6 in some order. Therefore, the original expression equals the square root of 12 plus the square root of 6. We can simplify the square root of 12 to 2 root 3. So the final simplified form is 2 root 3 plus root 6. In this lesson, we will learn a reliable algorithm to convert some cube roots that contain square roots into much simpler expressions. We will work 2 full step-by-step examples. And along the way, we will emphasize the algebraic pattern that makes the method work. The guiding idea is this. If you see a cube root of the form a plus b times the square root of c, try to write it as alpha plus beta times the square root of c. Then cube both sides and match the rational and irrational parts to get a small system for alpha and beta. Example 1. Evaluate the cube root of 38 plus 17 times the square root of 5. We assume it equals alpha plus beta times the square root of 5. Cube both sides and expand. Then equate the rational and irrational parts to get two equations. 17 is prime. The second equation factors as beta times 3 alpha squared plus 5 beta squared equals 17. So the clean integer choice is beta equal 1. Then 3 alpha squared plus 5 equals 17. So 3 alpha squared equals 12 and alpha equals 2. These also satisfy the first equation, which confirms the guess. Visually, the expansion naturally splits into a rational part and an irrational part with square root of 5. Matching those parts separately is the entire trick. Example 2. Evaluate the cube root of 7 minus 5 times the fourth root of 4. First, the fourth root of 4 equals the square root of 2. Assume the expression equals x plus y times the square root of 2. Cube and expand, then group rational and irrational parts. Set up the system by matching coefficients. We now look for small integers that satisfy both equations. Try x equals 1 and y equals negative 1. The first equation gives 1 plus 6 equals 7, and the second gives negative 5, both correct. Therefore, the cube root equals 1 minus the square root of 2. Let's simplify a radical expression by using substitution and recognizing a perfect square inside the square root. Here is our example. We will simplify the expression. A read as the square root of 4x times the cube root of x minus 4x times the cube root of x squared y plus x squared times the cube root of y squared plus y to the fourth minus 4y squared times the cube root of x squared plus 2xy squared times the cube root of y. Step 1. Use a clean substitution to simplify all cube roots. Let it equal the cube root of x, so x equals a cubed. Let b equal the cube root of y, so y equals b cubed. Now, rewrite it using a and b. Step 2. Evaluate each cube root exactly. The cube root of a to the 6th times b to the 3rd is a squared times b. The cube root of b to the 6th is b squared. The cube root of a to the 6th is a squared. And the cube root of b cubed is b. Replace those into the expression and simplify the powers. Step 3. Recognize a perfect square pattern inside the radical. We will attempt to factor the inside as a single square. Indeed, the inside equals the square of a cubed b minus 2a squared plus b to the 6th. Step 4. The square root of a perfect square equals the absolute value of the base. Therefore, a equals the absolute value of a cubed b minus 2a squared plus b to the 6th. Final step. Substitute back a equals the cube root of x and b equals the cube root of y. We obtain the simplified result. In this lesson, we will simplify a nested radical expression using a smart substitution and the cube expansion identity. Here is the problem. We want the exact value of the cube root of square root of 50 plus 7 minus the cube root of square root of 50 minus 7. Step 1. Simplify the inner square root. Square root of 50 is square root of 25 times 2, which equals 5 square root of 2. Replace it in the expression. Step 2. Make a clean substitution. Let A be the cube root of 5 square root of 2 plus 7, and B be the cube root of 5 square root of 2 minus 7. Then our target is a minus b. Step 3. Use the cube identity. The identity is parentheses a minus b close parentheses cubed equals a cubed minus b cubed minus 3, ab times parentheses a minus b. We already know a cubed and b cubed from the definitions. A cubed is 5 square root of 2 plus 7, and b cubed is 5 square root of 2 minus 7. Their difference is 14. Next, multiply a and b. The product inside the cube roots is a conjugate. Parentheses 5 square root of 2 plus 7 close parentheses times parentheses 5 square root of 2 minus 7 close parentheses equals 50 minus 49, which is 1. So AB is the cube root of 1, which equals 1. Now plug these into the identity. Let x equal a minus b. Then x cubed equals 14 minus 3 times 1 times x. Bring all terms to one side to get x cubed plus 3x minus 14 equals 0. Try small integers using the rational root idea. Plug in x equals 2. 2 cubed plus 3 times 2 minus 14 is 8 plus 6 minus 14, which is 0. Therefore, x equals 2, and so a minus b equals 2. As a quick check, substitute x equals 2 back into the derived identity x cubed equals 14 minus 3x. We get 8 equals 14 minus 6, which is 8, so the result is consistent. Summary. We simplified the inner square root, set a and b, used the cube identity, found ab equals 1, and a cubed minus b cubed equals 14, solved the simple cubic, and concluded the exact value is 2. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.